Today I'm going to talk about stainless steel's corrosion and its prevention in coronary stent. First, a quick overview of what I'm going to talk about today. Some background information of the stent, limitations about its application, and how to prevent this from happening, and comparison of possible solutions. And finally, a conclusion. Coronary heart disease caused by the blockage of artery is the main reason for many people's deaths in the world. Coronary stent is used to treat this disease. Here is an animation of the implantation of coronary stent. As you can see that a balloon is used to open the blockage artery, and after this, the stent is inserted to keep the artery from reblockage. Then the stent will stay in the patient's artery. Since the stent will remain in patient's artery, the material used is limited. From all possible materials, 316L stainless steel seems to offer an ideal solution for coronary stent because of the austenitic structures in the material shows strength and ductility combined with corrosion resistance and satisfactory biocompatibility. However, it is still difficult to limit the allergic response caused by the releasing ion due to any corrosion of the stent. Most of the time, nickel is the most important ion that will cause the allergic response in human body and will potentially cause cancer. As a result, different methods were applied and different materials were used to fabricate a proper stainless steel stent to prevent allergic response and toxicity of the material. There are basically two types of preventions to reduce the corrosion in the stainless steel. First is by surface coating, and second is to reduce the nickel composition in the stainless steel. Theoretically, surface coating can be used to improve biocompatibility of the stainless steel stent and to inhibit coagulation and platelet adhesion. One surface coating material is titanium dioxide. In this experiment, the properties of titanium dioxide film modified 316L stainless steel stent were investigated by using micro X-ray diffraction and scanning electron microscopy separately, and the open circuit potential were tested comparing with the bare 316L stainless steel stent. Figure 1 here shows the morphology of expanded stent. On the top is the titanium dioxide film modified stent under 4 minutes, and on the bottom is under 6 minutes. And as you can see from the figure here, there is no addition crack or particles on the stent surface. Shown from figure 2 here, the modified stent on the top is more positive than the bare stent, and the modified stent is more stable since it does not vibrate much after 200 seconds. Also, the potential difference between bare stent is much more higher than modified stent. As a result, the Columbia charge should be higher in bare stent compared with the modified stent. Figure 3 here is the polarization curves of the bare modified stent under 4 minutes and 6 minutes. The data above is calculated and indicating the outstanding electrochemical nobility and stability of the titanium dioxide modified stent compared with the bare stent. Compared with different morphology stents in figure 4 here, some pins can be observed from figure 4a on the left, which indicates corrosion, and some friction can be observed from figure 4c on the right, which indicates the certain thickness has a good protection. Expect from surface coating. Limit nickel in austenitic stainless steel is also an efficient way to provide an allergic response. Nickel release in human body will could potentially cause cancer. Similarly, research done by other people shown that at very low concentrations of nickel and cobalt ions, which could which will not influence on cell morphology, could cause significantly expression of cells adhesions. As a result, people want to manufacture low nickel composition stent using in human artery. People found out that high nitrogen composition will lower the nickel composition and manufacture new stainless steel. As shown in the table 1 here, for stainless steel that have a higher nitrogen composition, it has a lower nickel composition. Different experiments were done to compare with different mechanical properties and biocompatibility of the 316L stainless steel and with the high nitrogen nickel-free stainless steel. Shown as figure 5 above, nickel-free steel indicated less number of platelet cleaning than 316L stainless steel after long time dipping in fresh human blood plasma. As a result, nickel-free steel has better anti-platelet adhesion performance compared with 316L stainless steel. As the nitrogen composition increasing, the platelets are decreasing, shown as figure 6 above, where on the left it is the 316L stainless steel and the nitrogen composition increasing from 0.46 weight percentage from left to 0.81 weight percentage nitrogen to the right. The corrosion resistance of nickel-free stainless steel was also tested, shown as figure 7 here, and the results show that it had a comparatively best corrosion resistance with highest pointing potential. The mechanical property of each material for stent are listed in table 2 here. Both yield strengths and ultimate strengths of the high nitrogen nickel-free stainless steel are much higher than the stent using 316L stainless steel. It's about 2 or 3 times higher in strength and the same level of plasticity. In conclusion, the high nitrogen nickel-free stainless steel has excellent mechanical properties, sufficient corrosion resistance, and satisfied biocompatibility. It could say that the high nitrogen nickel-free stainless steel stent is a proper way to solve the corrosion of the stent inside the human artery. That people could use biodegradable materials to fabricate the stent, because if the material is biodegradable, we do not need to worry about any corrosion of the stent, and the corrosion may be even help for the stent to be degradable.